All right, welcome to chapter 12. We are going to be doing the Anova. So the name Anova comes from analysis of variance. We're going to be looking at three different types of Anova today. The one-way, which is looking at one factor, the balanced two-way, which has more than one factor, and also the blocked version of that, and then the multi-factor ANOVA, which is going to also have what we call an interaction factor. This sounds like nonsense until you actually seen them done, but basically we're going to be doing what I used to call the sledgehammer test. I also used to like to write it like this because it's analysis of variance, because V get capitalized. The reason I used to call it this is because, well, when I wasn't sure what to do to my data, I would just try the Anova on it because, well, it'll do lots of different stuff, and you'll see that there's quite a bit of variation in what it possibly can do from what we see today. The other thing I would say is that make sure that if you don't have access to Minitab, you go to our Week 9 folder because, well, I've got how to download it and install it in there, because I'm not sure who among ye will have a Minitab at this stage versus who among ye who already do. I am also including some Excel in what we do today, and I will be attaching those Excel files along with this video. Cool. So let's talk about our objectives. We're going to look at two different types of ANOVAs today. We're going to be looking at the single factor and the two factor. We're also going to be doing some randomized block design, which is just how you develop the Anova in a slightly different way. And I'm also going to be talking to you a little bit about where the Anova comes from and some logic behind it. I'm also going to be doing a little bit of Excel today, just in case some of you don't have access to Minitab. So there's that. However, if you have access to a computer, you can install Minitab on your computer, and I did leave directions for that in your Week 9 folder, so make sure you check that out and install Minitab, because in my opinion it's easier to do on Minitab than it is to doing Excel. But just in case you don't have access to it, we're going to see some Excel today. So I don't know if you realize this, but a lot of time you spend in Statistics 1 is on observational studies. A lot of it's focused on let's look at proportions and counting stuff and things we can observe from pre-existing data. So for instance, I have an example here of a company collects a variety of data via registration or warranty cards. So if you've ever registered an electronic device that you've bought, like a vacuum cleaner or a computer, that's definitely what this is talking about. The data might be utilized later on in an observational study that seeks to discover a correlation between variables in the data collected. So maybe you notice that more people in a certain age group buy one model of your vacuum more than the others, that kind of thing. So there's two types of observational studies out there. There are what are called retrospectives and prospectives. Retrospectives are kind of cool because they're always using historical data that someone else collected. Some of these go back thousands and thousands of years. The most interesting retrospective I read recently was these monks that have been recording the amount of ice thickness on a lake in the Himalayas for like 1700 years. And sometimes their measurements don't make a whole lot of sense because they were measuring it with sticks, and it's interesting, depending on who you are. And then the example I gave you here is a little bit more businessy. It's focused on using credit card records to identify, relationships and how you can get new customers. So if you notice you're getting a lot of a certain type of customer, you can go out and find those individuals in the population and offer it to them. Sorry, my headset's being squeaky. And then prospectives are trying to look at things in advance. So it's looking in the future. So retro is looking back, so like retro clothing, and pro is going forward. So if you want to look at smokers and see if they are going to have a higher occurrence of emphysema than runners. So notice we're comparing groups with this as well. Anyway. So where does the Anova come from? Basically, the Anova is, I want to compare a bunch of groups and ask myself, is there evidence for differences in these groups? And we're going to be looking at this specifically from the quantitative perspective. So be thinking like the one sample T or the two sample T tests, because this is going to be like what's a good word for this? Like the grown-up version of those tests, because it will be able to test any number of means. So how it's going to do that is it's going to compare them all to each other and ask, is there no difference between them, or are they all the same? And then the alternative will be at least one is different. Now, you'll notice down here that I didn't type out all of what this could be because, well, to be honest, if I'm going to have to write at least one is different, that means I have to write, well, 1 is not equal to 2, or 1 is not equal to 3, 4, 5. I have to write so many ors here that it's just not practical for you to write it any other way. At least one has to be different. Yep. One thing that we'll see about the ANOVA that's not so pleasant here is that, well, it doesn't tell you which one is different, so we're going to also need a little additional what we call ad hoc or after the fact testing to see who's the one who is different. All right, so here's what the ANOVA is going to do for us. I've got 2 sets of box plots here displaying some different changes that you might see. So take a moment to look at these 2 and ask yourself what you might be observing. Hopefully you notice that the first group is different from the second group, not just because you can see that their numerical scales are different, but our ANOVA is going to be able to detect both of these. So I'm actually going to start with the one on the right. So you look at all these box plots, you notice, oh, they all look to be about the same shape, but their centers are all very different. Their medians are all very, very different from each other. So what we want to say here is that, oh, if we look at the variation within my groups, aka their shape or spread, they look to be about the same. But when I look at their means or their centers, they're all different. We see that? So center, oops, different. That D came out terrible. Shape, same. And then over here, you'll notice that, oh, it looks like their centers are all pretty close to each other. So when I say center, you should be thinking like mean or median. In this case, it's the median. But here, their shapes are all very different. Sorry for the cursive, that's to get it going fast. Some of them, their spread is very, very wide. Like this one has a huge IQR compared to the others. This one has a tiny one, yeah. But then these 2 almost have the same IQR. They're pretty close to each other. So what's interesting is 2 of your groups appear to be the same, and then 2 of them appear to be very different. And we want to have a test that will actually do all of that, detect differences in spread and differences in center when I look at my groups. How different are my groups? And the ANOVA is going to accomplish that for us. Mostly by looking at centers, but you know, it does a lot of stuff. It's I used to call it the sledgehammer test when I was a student, because when I wasn't sure what to do, I'd just pound the ANOVA onto my data and see what happens, because it does so much for you. Or as I like to say, if you don't really know what your data is doing, try an ANOVA. Anyway. So we're going to start off by looking at what's called the one-way ANOVA, which is when we are looking at only one factor. I'll talk to you about what a factor is in a second, but basically this is the setup for the one-way ANOVA. It's what I've been looking at so far. You'll see how the two-way and the balanced look a little bit different than this. So we're going to be taking a look at the one-way ANOVA. It's called one-way because it has a single factor, and a factor is always just going to be a qualitative variable that creates our groups. And then the values or categories within that qualitative variable create our levels. So some of these names come from medical science or the original use of the ANOVA, which was in medical experiments. Sorry, I was just trying to remember exactly where the first time this came from was. Yay, history. So you'll have a factor and you'll create 4 groups from this if it has 4 levels. And then inside your groups, you'll have all your observations. So these are like your quantitative values. So maybe this is like the number of times people have sneezed that are in group number 1. I have no idea where that came from. Group number 2, group number 3, group number 4. I really don't like calling them 1, 2, 3, 4. I like A, B, C, D because these usually represent something qualitative, not quantitative. And in this case, since they're all equal in size, we would call this a balanced design, since the groups I'm comparing have the same number, which makes it easier to detect some things about their distribution. Okay, so here's an example where we look at levels, factors, and sizes. So a sandwich shop is interested in testing to see whether the mean value for its customers' orders is equal in the company's 4 store locations. 8 orders from each store are randomly selected. So here, my factor is going to be, hey, what's the order value? That's the quantitative variable I'm going to be looking at. And then the 4 levels within that factor are the locations. This is actually incorrect compared to everything else I've looked at. Oh, that's bad. So this isn't your factor. This is your response. I have this backwards. Oh my God, that does not look like a word. Sorry. The worst part is when you use PowerPoint, you can't edit any of this. So this is what we call our response. This is what we're trying to measure differences. Our factor is actually the locations. And then the 4 locations are what make your 4 levels. And then the sample size is the 8 samples you took at each store. Sorry about that. Anyway, so suppose this is our, so notice how my factor is store locations. Good job, teacher. Anyway, so then I've got my 8 customers randomly selected from each store. So this is not the same customer. It's just the first one I selected from store 1, the first one I selected from store 2, this first one I selected from store 3, the first one I selected from store 4, because clearly no. And then if I did the mean of this, the mean of that, the mean of this, and the mean of that, I am comparing all of them, asking, are they all the same? AKA, are they all not equal? Yay. I'm sorry, not all are the same, not all are equal. So really, I'm hoping you notice that the Anova is the same as every other hypothesis test. Its ho is some kind of statement about sameness or equality, and its ha is, well, whatever else could happen. But the difference between the Anova and every other test you're going to see is the ho and the ha are always the same. All right, factor. Yep. The quantity under examination in the experiment for possible causes of variation. So the different groupings that could cause the variation that we're seeing. The levels, these are the categories that create our groups or strata or whatever other factor you could possibly look at. These create your different groups. Now these might all be different populations. They might also all be one population that you've separated out by something of interest. And in a balanced design, all sample sizes are equal. I really should have put this sooner. Regrets. All right. Assumptions and conditions. The AKA check yourself before you wreck yourself. The things you have to know are true to be able to use the Anova. Now the Anova, since it's a more powerful test, does have a larger number of assumptions. Prepare yourself for that. The first thing is that you need to check that all populations are normally distributed. So that's that normality test that we've been using in Minitab. The population variances are all equal. This is a big assumption and might not be true. Good times. Your observations are independent. This has to do with your sampling method. If you've sampled well, you don't have to worry about this so much. And then the last is that your data is interval or ratio and level. This means that it has to be quantitative. This is a quantitative test. In case you forgot, interval and ratio variables are ones that, oops, that's not where I want that. This tells you you have to be quantitative. So if you try to, I can't speak and write at the same time. If you try this test on something that's non-quantitative, it don't work, or at least it shouldn't work. Now I know some of you like to change your variables from being things like yes, no, maybe to 1, 2, 3, 4. That is, those two did not match. 1, 2, 3. That does not change the fact that that data is not interval or ratio and level because it doesn't have units. Don't do that. That's bad. All right. So here we go. If you have a bunch of populations like 1, 2, 3, 4, like we've been doing, hey, you know, they all look fairly normal, hopefully, and hopefully have about the same variance. I'm hoping you notice my normal distributions here all look to be about the same size. What do I mean by that? They'll have about the same spread. So like this one is the same width as this one, is the same width as this one, is the same width as this one, is the same width as this one. That's like saying that, oh, look, they have the same standard deviation, aka they have the same variance. They're spread about the same. Yay. and they all look normal. Now, in this drawing, I've made it sure that like my means aren't close to each other. Good times. So hopefully my Anova would detect that. Good times. Now, if the Anova is true, they should all line up or at least be close enough to each other to where it seems reasonable. This is the assumption of the Anova when it goes to do its test. What it's saying is that, oh, look at all these groups, they have the same mean, they're all equal to each other. And they might not be, depending on what your sample data seems to show you. All right. So if the null hypothesis is true, we're going to be looking at identical distributions. They all look the same. That's what it means. When I say distribution, I mean most shape, spread, center, everything about it. And then hopefully it'll be rejective if there's some sort of substantial difference in either spread, shape, or center when it comes to our distribution. And it might be one that's different. It might be all three of them are different, or four of them are different, or it might be pairs where a couple of them are similar or the same. And the Anova is going to detect that. And then you're going to need an extra test on top of it to determine who's the actual different one. All right. Some logic behind this. This is going to be a little bit of a tough row if you're somebody who's not very mathematically minded. I really wish we were doing this person. Okay, so when we start looking at the Anova, there's a bunch of things we have to compare. So since we have a bunch of groups, we want to know, woohoo, are there differences between the samples themselves when I compare them? Is there differences within each individual sample? And overall, that will create my total amount of possible difference. Now, there's a word here that you maybe have never seen before, sum of squares, but you've definitely seen a sum of squares before. Remember back in the day when you learned about standard deviation, you're like, oh, I gotta take x and subtract this mean and square it and then sum it? That was a sum of squares. And then we had to do extra stuff on it to make it not suck. Standard deviation. Whee! So a standard deviation is just a sum of squares. When you're looking at a sum of squares, you're trying to detect how different are things. So in this case, I was asking how far is x, all my data values, from the mean? Oh boy, but if I add all those up, I'd always get 0, so we squared it to make it positive. So when we're doing a sum of squares, that's what we're focused on. How far away are these, and can I measure that? All right. So I've got all these data values. So I'm doing my sandwich data again because it's a fairly small data set and it should be easy for you to see what the total variation looks like. So now I'm going to look at how different are they between groups and within the groups, and then ask myself, how much total variation do I have in comparing those two things? So be thinking, why am I comparing the groups to each other? I want to see, are they all different from each other? Kind of like that second box plot. And then I also want to see, how do they all compare within each other? Like, how are they spread? Let's do this. Woohoo! So we're going to need something called the grand mean, or as I like to call it, the Mac Daddy mean. It's the mean of means. Okay, that sounds insane. What is the grand mean? That's this guy right here. So it's like x bar bar. When you look at this, it's just add up all your data. So that's adding up all of these and doing their average. It's the average of all of the data. And then what we're going to do with that is we're going to compare all of our data to the mean of all the data and ask ourselves, how far off is that? That's the total sum of squares, or SST. So that's what this is doing. So when it says Xij, the I is representing the group you're in, so either first group. Yep. And then the J represents your customer number. So what this is doing is adding down, oh, that line didn't line up, the first group, and then it moves into the second group when I is 2, and then third group, and then fourth group. So you can see it doing that in here, like, oh, 4.10 minus the grand mean. How far are they all apart? And it looks like it's 288. Woohoo! If you're scared of doing this calculation, Minitab is going to do it for you, okay? And it's just going to label it total. It's fine. Well, total sum of squares, but fine. All right. Then next up, we do the mean of all the groups individually. So notice down here, I have the mean of the first group, or sorry, first store, second store, third store, and then fourth store. And don't forget, grand mean, double X guy. Cool. What are we going to do with this? We're going to use it to measure the sample variation, or the variation between the groups, so comparing them all to each other. So how you do that is you're going to take the difference of your means by sample size. Now notice this n is here because if my samples were different sizes, that sample should have a bigger effect overall when I compare them to each other. Get the idea? In my case with the sandwich shop, it's balanced. They're all the same size, so none of them is going to have a bigger effect than the others. So we're asking ourselves, when I look at all of these together, the overall mean of all the data, how far is my mean of one store from everyone else? Yeah? Between the groups. Yay. So we're going to take each of those means. So I'm looking down at the bottom. So this mean minus the grand mean and times the sample size. Remember, these are all size 8. Oh, and don't forget to square because we're doing a sum of squares. Woohoo! When you do that, you get 22. This is usually a nicer looking number than the total, just so you're aware. Not always, but usually. Okay. Now for the harder one. Oh boy. Within each sample variation, this is trying to measure the dispersion. So think spread for dispersion. How far away is everybody spread with each other? This is the second part of what the ANOVA does. You know, I just compared my centers. Now it's going to compare the spreads. So how we do this, and this is a little bit more difficult, is within each group, I'm going to be doing a standard deviation, kind of. So notice this first part of the box. If you hadn't seen like that second sum would just be the first step in doing the standard deviation. How far are my values from the mean? And then square it, add them all up. Yeah? And then the second part is like, well, we need to do it to all the groups because we need to measure it within them. Yeah. So it's doing that, but then also adding it to all of, well, adding all the groups together. Another thing you can notice is this is going to be the same thing as if I just took the total and subtracted the sum of squares between the groups. Woohoo! So this one is a longer calculation by quite a bit. So if I take each mean and subtract it from each data point, so notice in like store number 1, I'm going to start with 410 and subtract its mean, square it, add to that, moving on to customer number 2 in store number 1, and so on and so forth. So yeah, you just do it to all of them. And then you go on to store number 2, 3, and you're done when that's all done. So notice that's what you get out of that. And then a fun thing to observe about this is, oh yeah, it is just the difference when you look at all these values. Another way you can do this is usually the total is easy to calculate and the between groups is easy to calculate. So usually I won't actually do this calculation. Instead, I'll just do the subtraction of the two of them because it's a little bit easier. But again, Minitab will do all these for you. You do not have to calculate this by hand. Moving on. So now that I've got the sum of squares partitioned, I've got the first part. So if you remember, I was talking about the standard deviation and how, oh, how do I really do standard deviation? I, do square root of sum of stuff minus a mean. I'm being vague about my mean here. Squared, because I have a bunch of means floating around, divided by n minus 1. So I've essentially done like this part. And now I'm saying like, oh, well, how can we use this? Well, I'm going to do the other stuff. The other place you see this get used is like when you're actually calculating a mean. I'm going to write the population mean for this one. I add up all the stuff and divide by how many I have. So I've done a sum. Now I'm going to average some things. Woohoo! Okay, next up, we're going to do some means. That's what I was talking about. On average, how much am I spread? Or how much total do I have in the sum of squares, or how far apart everything is? We're going to do some means, both between and within. So I'm just going to take everybody and divide by their sample size. So since the first one was about looking at all the groups compared to each other with their grand mean compared to their individual means for the groups, the degrees of freedom for it is going to be the number of groups that are present. So that was k minus 1. So the mean sum between is going to be the sum of squares between divided by the number of groups that you have. The mean square within the samples, or MW or MSW, this is also sometimes called MSE, is just going to be looking at within. And so that's going to be the number of total that I have of all of my groups subtracted by k. Another way that you'll see this occasionally in older books is instead of using NT, which is just all the little n's added together from all of your groups, not plus, ... until you get to all of your little groups k. The other notation for this is just a big capital N, since it's just the size of all of your data. Just to keep that in mind for those of you who have looked at other textbooks. Woohoo! All right, so I've got my means, and now I want to compare how large they are to each other to detect who might possibly have the largest difference. So this is going to be a ratio test, and to do that, I'm going to need something new. I'm going to need what's called F. So we have seen other test statistics up to this point. We've had a T, and we've had a Z, and now we need a new one because this one is a ratio. Now this is different from T because it's just comparing how big I am between my groups to how big I am within my groups. And what we want is we want to have an F that's large. So what makes F a little bit different from the others, let me change colors here real quick to like a blue, is it starts out at 0, which is a little unclear from this graph, and then it gets larger depending on how much bigger your numerator is than your denominator. The larger your F value is, the more likely you are to reject the null hypothesis, because that means the more unusual you are when looking at the centers. That's why this is a test of means. How far are my centers from each other? Well, that's measured by my mean square between group. So what's happening is if this is really, really large, well, then you're going to have a really, really large F. So it ends up over here for your test statistic, and therefore you would be rejecting. Hopefully it's in the region alpha kind of thing over here. Alpha, reject region. Usually we color this. I wish I'd have drawn this better. Oh, that's right. I stole this from your textbook. That's why I have to have all the copyright down here. Anyway, so the bigger F is, the more likely you are to reject. One thing that's nice is F starts at 0. It's always positive because it's using sums of squares. When you add up things that are squared, everything's positive. All right, this is what is called the Anova table. It takes everything we just did and organizes it. Hopefully you noticed by looking at this table, there are some things on here you've seen before. As a reminder, to do MSB, you just need to take SSB and divide by k minus 1. So usually when we're doing these tables, we can just take the previous values and divide them by each other to get this. Previous values, divide them by each other to get this. And oh look, this one's just these two divided by each other. So it's a bunch of ratios. You need to think of F as a ratio. Anyway, and then we decide if we're going to reject our hoe if our F is too big or too unusual when it comes to looking at alpha. All right, so here's our sandwich example where I've finished filling out the table. Now my F here is not very big. It's 1.03, which is kind of disappointing, to be honest. I was kind of suspecting the sandwich shop's orders were probably all the same, because how many sandwiches do people really need or really eat? I don't know. I'm just one of those people. I don't know. I was kind of hoping something would happen so I could be like, reject things, math. Whatever. Oh, talking in a room alone by myself is weird. Okay, so this, I'm not going to lie to you, I use technology to do this. So I took my results from my Anova table, my raw data, and I took my level of alpha and asked Minitab to produce the top 5% level of F for that. I'm going to show you how to do that in the Minitab video this week. And I got 2.95. Hopefully you notice that my sample is 1.03 from earlier, which means it's over here. Yeah. Bunk. Which means that it's not in the rejection region. We're going to fail to reject. It looks like there's no difference in average order between all of my 4 stores. Good times. That's it. Yay. And now an Excel example, because I warned you this was coming. If you're not big on Excel and you find it confusing, you might want to skip this part of the video simply because, well, you know, Excel ain't for everyone, and that's okay. Suppose we have a health products company that is experimenting with 2 new weight loss products. This is going to be awkward for all of you. To determine the effectiveness of these products, 300 people, all of whom were 30 to 40 pounds overweight, see how we're controlling this to make sure they're similar, were asked to participate in the study. Of these, 100 were given a placebo. If you don't know what a placebo is, it's basically a inert pill that does nothing, but because they're also getting a pill, they think it might do something, and that'll take care of the psychosomatic effects that people get when they have a placebo or think something is happening. And then 100 were given the first product, and the other 100 that remain after that were given product number 2. None knew that should be a K, what product they had been receiving, and then after 6 weeks, they looked at the number of pounds they had lost. Now, as you know, weight gain and loss has a lot of factors other than this, like gender, age, activity level, diet. These should have been also controlled for in this experiment, but clearly were not. Anyway, so what they want to see is that if they look at their weight lost, if it's positive, the subject lost weight, and if it's negative, then some people gained weight. Now, one of the problems with long-term studies is often people will drop out or leave the study if they decide they don't want to participate anymore. In this case, you'll notice that when they were done with the study after 6 weeks, they only had 89 placebo, 91 product 1, and 83 product 2. This happens a lot. I'm going to provide the Excel file for this. It's called Best Health. And here are my null and alternative hypothesis for this. I'm going to be using an alpha of 0.05. Now, one thing you might notice about my notation here, and this is something that we've been doing for a while, but, you know, is important to note, I've labeled my groups according to a way that can help me tell who is who. So P for placebo, 1 for product 1, and 2 for product 2. And here, notice that, like, as the experimenter, you don't know which product is which, and that's also important when it comes to a blind study. And we're going to see if any of these means are different, and hopefully it's not the placebo. But that could also mean that your 2 drugs were both effective. I know that you might be interested in medical studies. One of the things I want to keep important for you when you look at this is that when it comes to healthcare, and this is something that I've seen them say on movies and TV that is absolutely not true, we can't not give somebody a treatment if they're dying or sick. So in general, when we are looking at studies where somebody is ill, we won't have a placebo. You will only be comparing 2 products to ask which one is more effective. So if you have somebody who, you know, what's something that won't kill somebody that's bad? Scarlet fever, for instance. Actually, people die from that. That was a bad example. Something that won't hurt, that is serious enough to where they wouldn't use a placebo. Let's say you have shingles. It's a very bad disease because, like, it spreads like wildfire. It's not great, and it also makes you itch like crazy. I haven't had it, but my mom had it, and boy was she miserable. Anyway, when you have a disease like that, you really want treatment. You don't want to go untreated. So that would be a case where they would do like product 1, product 2, and no placebo. Same thing with cancer patients. They can't elect to not give them treatment. So they just compare effectiveness that way, which kind of, you know, is the moral way to handle it. Why did I talk about that for so long? I have no idea. Anyway, so in the weight loss example, I went ahead and calculated this for you. I will show you how this is done in Excel in about 2 seconds. So if you're wondering where are these values coming from, patience, please. So I have the F statistic right here that I got from Excel, and then I have the critical value for F. This was me putting in 5%. And then asking Excel to produce the F critical value for me. So notice that's the cutoff for when something is going to be considered unusual, and this F is like way the heck over here. So clearly 1 or 2 of my groups are very different from the others. You'd say, the weight loss amount is not all the same on average. I wonder which of these is doing something so different from the other. And that's where we're going to need something called the Tukey test. So speaking of Tukey, I thought this was later. Oh, I love PowerPoint. I hate it, not gonna lie. Anyway, so the Tukey-Kramer test we're going to be using is what's called a multiple comparison test. It's going to ask ourselves, are these 2 really different from each other, or these 2, or these 2, is these 2? It's a pairwise comparison test. So since we decided, oh, clearly one of our products, or maybe the placebo, appears to be relating differently thanks to the Anova, I want to ask myself which one is different, because the Anova didn't give that to me. And this is something fairly typical in math. We don't go looking for answers where they don't exist. So really what the Anova does for you is it says, oh, look, one of them's different. You should figure out which one it is. And then a Tukey test is going to do for you, oh, it's this one or that one that are similar or different. So the first step is doing the Anova. The second step is always doing the Tukey. And here's some details of how the Tukey works. It's a 1-button click in Minitab, and it's not that interesting. So I'm going to not go through this because it's just a bunch of pairs tests. So it's like doing a bunch of little T's because it's not that interesting. Anyway, so what the Tukey's doing is it's going to try to compare the groups to each other in pairwise differences, and that's what it means when it says pairs of treatments. So it's essentially doing the 2-sample T, put to all the combinations at once, and then reporting to you who was different. And this actually looks pretty cool on Minitab, so I'm looking forward to your Minitab video this week so you can see that. Anyway, so the Tukey test, this is bad because the Kramer version of this is interesting, but I'm not huge on using it. It's built off of Chebyshev's theorem, which isn't the most accurate thing in the world. It can only give you a maximum, and that's why you see this inequality in here of, oh, I think it might be bigger than that, or it might be smaller. But that's useful enough if you're looking to just compare two things. Is this going to be positive? Anyway, I'm trying to ignore and not do these values because it's really silly to make you do all of this when Minitab will just give it to you in 5 seconds. Anyway, so what you do is you take your two samples, I and J. So like if this was like product 1 and product 2, you take their two sample size, you take your difference between them and average it. So this is just like saying, oh, they should all be spread on average the same for these two. And then asking yourself, is it going to be, my mean is going to be bigger than that from on average for the difference between their means. Whew, that was weird. And I just flat out state the degrees of freedom for this because it's real confusing. How do you calculate that? It's not very easy. And it's built off of that same, what was the name of this? The pooled standard deviation from the two sample T. It's actually the same one that's supposed to be a D. DF. I wish I could erase effectively. So if you're wondering why that looks so weird, it's because it's that horrible formula, if you remember it. Anyway, so you've put in all those values, you get the range is 1.85, and then you look at the difference in the absolute value, and you get 4.2, and you notice, oh my gosh, that is bigger than that, so you conclude these two are different. So evidently, product 1 is different from product 2. Or no, wait, this was placebo versus product 1. Sorry, I forgot that that one's the placebo. Whoops. So it appears I found a difference. Now, if you want to do this by hand, you are going to have to do this at least 3 times. You're going to have to compare the placebo to the product 2 to product 1, and then the placebo to product 2. I don't want to ever do that because that's just way too much work. So I'm going to let Minitab do this. And it's actually really easy to read the results off of Minitab. So I did go through and do this all by hand because evidently I hate myself. And here's what you get. So hopefully you notice there is a significant difference between placebo and product 1 and placebo and product 2. But when I look at the two products compared to each other, there is no significant difference. So evidently both products appear to have a difference in weight loss compared to doing nothing, aka the placebo, but they behave similarly. So if one of your products was cheaper to produce, that's the one you should go with. Woohoo! Let's look at a complete block analysis. So blocking is something that you have to watch out for because not all of your factors are going to be things that you can design and control. So be thinking things like age or gender. They're going to be ones that your observed responses are going to take care of themselves. So if you wanted to ask yourself, maybe like, do men buy my product more than women? That would be the example of a block. Blocks have almost the exact same assumptions and conditions as doing a one-factor ANOVA. You know, notice I still have, I want to be normally distributed, and I want to have equal variances, and everything needs to be independent, and I need to have interval and ratio. Woohoo! It's the same test. It's not shocking. These are all the same. The difference is how you get your data is different. So suppose you want to test 5 routes through 3 different cab companies and see if a difference exists. You can't control how the which cab company you're getting. You're going to determine maybe like the best training program out of 4 choices for various departments in the company. You can't choose who's going to go to which training program. There's a lot of non-choice in a block. Yay! So when you look at this, you're going to want to compare a bunch of different things. You want to see, do my factors have an effect? Does my block have an effect? Or is it within all of my levels when you look at the combination of all of them? This is a little bit weird. So it's kind of like, we're going to do the 2-factor in a minute. It's kind of like you have 2 factors. You want to ask yourself, is it factor from the block, or is the factor from, is the factor from the first factor, this other variable you've got, or is it from this one? So you want to ask yourself, when I look at combinations of these 2 variables, does it have an effect? Anyway, so the way you look at the blocking squares, God, does that sound weird? Oh no, it's squares for blocking, is you treat them exactly like a factor. So I'm hoping you notice this looks exactly like the one for just a factor, which was, oh my gosh, no, we called this within. That looks like not a W. I was looking at the sum for all the different groups. So that should be a K times their size. I used a J here because I'm awesome. XJ minus the grand mean. It's the same idea is what I want you to get from this. So it's not like I'm doing something crazy new, you know? Then you go through, do all your ratios, exact same idea. The difference is that when you look at your degrees of freedom, since you have two factors here, you basically get the degrees of freedom from each of the previous factors multiplied by each other. And here is your stuff. So when you look at this, here's what I want you to notice. You have two F's, because essentially what you're doing here is two tests. Is it the blocks that are causing the difference, or is it the natural difference between the factors themselves that cause the difference? So this essentially has two hoes. Yeah. Not mind-blowing. We're going to look at one in your notes where there'll be three hoes, and I like to teach that around Christmas time because it's ho ho ho. Ha ha ha. Yep. This is the most boring thing I've ever done. So you'll have your primary factor and whether or not it has an effect, and then you'll have your blocking factor and if it has an effect. So you want to ask yourself, is my block that's causing a difference, or is it my main factor that's causing a difference? I'm also going to show you how to include an interaction term to say if they combine to cause a difference, which usually they don't with a block. All right, let's look at an example of this, because boy, was reading that going to be the, like, reading craziness. This is where you're going to see an example that makes more sense, hopefully. So I've got a professor who has developed 3 different midterm exams. This is something that I do myself, so this is a little bit of a faux example, but hopefully something you can relate to. They're all graded on the same scale. Before she uses the exams in her live class, she wants to determine if the test will yield the same mean scores. To test this, she has a random sample of 14 people selected, and each student will take the test. So the controls or the blocks is the students to guard against the overweighting of good students being randomly assigned to any one of the exams. So you look at the students individually and organize them based on their previous performance. That's what we're going to be testing against. Because if you are giving a test to a bunch of people and you magically give test 3 to all the students who had like C's and D's, then clearly that test is going to look different than the other 2 tests, more than likely, unless, you know, all of them have a sudden change of heart and decide to study real hard for this test. I don't know why I laughed at that. That was inappropriate. Whee! So here we go. So we got our 14 students, exam 1, exam 2, exam 3. So keep in mind these are not the same 14 students. It is 14 different students that hopefully are all academically as varied as each other. And then I've got my block means and my treatment means. So treatment, remember, that is just for by factor or by level. And again, the word treatment comes from the history of this, where these are just my levels. We're not treating anybody with anything. Nobody's sick. Everybody's fine. Awkward. Yay! So I've got all my sums of squares. Again, I did this using Minitab. If you want to do this manually, you can. I do not encourage that. Boy, will that take you forever. I've referenced which equation I've used for each of these. Hopefully that helps you if you want to do this by hand. Those of you who like to use your calculator to do this, you can do an Anova on your calculator, but it's difficult. Let's just put it that way. Anyway, so I've got my primary tests. The 3 tests do not all have equal mean scores. The 14 students do not all have equal mean scores across the exams. So I got my 14 students are not the same. Woohoo! So then I look at my F's. This is what's interesting. Oh yeah, there's a small f, so that's going to be something that's probably not going to be rejected. And then I've got a big F right there, so it looks like that is going to be rejected. So that's interesting about this test. Yep. So taking a look at this, you're like, ooh, okay, who's going to be rejected? It looks like the between blocks, since I have a rather small f when I calculate the critical value, although it's not very big because we have a small degrees of freedom for this one. My F is probably like here-ish. Yeah, because that's about a little over 2, and this is like under 1. Anyway, so it's clearly not in my rejection region, so I would conclude that the blocking on the students was not effective. I didn't evidently randomize my sample enough. My students are not different enough from each other. That was not good. So since I'm failing to reject... No, wait, I said that wrong, because with this you'd be like, hey, do not reject my null hypothesis. It looks like my students are all the same. My blocks are all similar to each other, and therefore my blocking was not effective because they all looked about the same. All right. And next up, we're like, oh no, this is the thing that you would be terrified by if you were the teacher. When I look at my 3 different tests, it appears that I would be rejecting the null hypothesis for that. It looks like my 3 tests do not have an equal average, so that means that at least one of my tests is different, and that difference is significant. So that would mean that maybe you've got one test that has significantly harder questions on it. Maybe you have 2 that are really similar in difficulty, and then the other one is a lot harder or a lot easier than the other 2. So it looks like you need to revamp your tests. Interesting? I hope so. All right. Let's do an example using Excel. So suppose we have a bank that has 3 appraisal companies and they are asked to appraise homes. This is something you have to do before you get a mortgage. Managers are interested in whether or not the 3 companies appraise properties equally on average. To test that, the bank selects 5 different homes from each company. Now that's a kind of small sample size. Sorry about that. And then we're going to do a blocked test on this. So in particular, you'll notice that my numbers are in thousands to, just make these easier to deal with and look at. Yay! So if you want, you can open the 2-factor Anova without replication file, and you'll see these results in there. You'll notice that my p-value is super tiny for this. Hopefully that'll be okay. You can take this file and make it bigger to do stuff with larger samples. So you notice that this is 1, 2, 3, 4, 5. So if you want to use this Excel file, that will work well for you. If you do not have the data analysis button, you can download the data analysis pack for Excel to do this. It's free. Don't worry about that. Anyway. So then you want to ask yourself, is the blocking effective? Do the homes have... The 5 homes do not have mean equal measured assessments. Yay! So you look at the F value for this and it's freaking enormous, so you're very sure you're going to reject. In fact, I wouldn't even probably do the critical... No, that's bad math. I would do the critical value for this. Anyway, so you would conclude the blocking on the properties was effective. They all are different from each other, or are unique mean assessment items as far as comparing the 2. Or sorry, 3. There were 3 mortgage companies we were comparing. Then you got to ask yourself, for my primary test, do my appraisers appear to all behave the same way? We look down at the p-value and the f-value for that. Now, this f-value is fairly small, but you would want to calculate your critical value, and you'd see that it was still in the rejection region, so you're going to reject the null hypothesis, and you'd say, it appears my appraisers, they don't behave the same way. They are different, at least on average, so that's not a good thing. Or maybe it is a good thing if you're a bank and you want to have one, appraise more than the other. Actually, that's kind of bad. I would probably stick to the more consistent of the appraisers if that were the case. Why do I have this in here? Oh, it's just a graph of those 2. Yay. I thought I deleted this. Fisher's least significant differences. No, we're not doing this. Ignore this part. Sorry, I got rid of that. That was not supposed to be in here. Blah, blah, blah. Anyway, sorry about that. I thought I had deleted those slides. I'll make sure I delete them from your notes because they are completely pointless for you. All right, let's look at 2 factors. So the biggest thing about the 2-factor is that not only are you going to have factors A and factor B that you'll be comparing, but you'll be looking at their combination. So we're going to look at an example where we're going to compare, like, if you ever have used a mileage credit card where they give you back like so many flight miles for every like dollar you spend, and age group. These are very popular with the older generations, especially like the silent generation and God, what was the one after them? the baby boomers. They are not so popular with millennials, zennials, and Generation Z. I'm a zennial, so I'm going to mention them. Live with it. Microgenerations unite. Anyway, so you essentially are going to have 3 sums of squares you're going to be looking at for this. And because of that, you're going to have 3 hoes. You're going to have, does factor A contribute? Does factor B contribute? And do they combine somehow to make some kind of difference? Because it might be that when you look at factor A alone, it is different. It might be that it's factor B alone that is different, but it might be certain combinations of the two that have an effect. And then this last one is just our leftover of comparing the groups all to each other. It's, you know, often just called the error, where it's just where the E comes from. Woohoo! All right, so here's what we're looking at. We're going to split this into 4 pieces: inherent variation, our groups, and then our interaction factor. So there we go. So if factor A had like 3 levels, factor B had 2 levels, then the combination of the 2 of them would produce a degrees of freedom of like, okay, let me give you a more specific example of this. Let's say we're going back to the weight loss one, and factor A was just, you know, the placebo, the pill number 1 and pill number 2. Then this would be a 3, and you'd subtract 1 and get a 2. Now let's say factor B is they decided, hey, let's look at gender and see if the pill is different for men and women, and or people that don't prefer to identify as a gender, so they're, or don't identify by the 2 binary genders, so they would have 3 options there as well. So then that degree of freedom would also be 2. So then the interaction factor would actually have 4 groups. It'd have it'd have degrees of freedom of 4 because it'd be 2 times 2. But in reality, this would actually have 6 groups. It would have what thing were you given? Was it placebo? Product 1, product 2, and then what gender do you identify as? Male, female, or non-binary. There we go. So that's how you make your, well, that would be 9 actually. I said 6, that's wrong. And then the leftover is, well, just the difference of those. Now, the 2-factor ANOVA is a little different with its assumptions. So you have to look at each combination of pairwise factor levels for normally distributed. So the example that I just gave had 9 different combinations that it could do. So there would be 9 you'd have to check. Yikes. It's not that bad, I promise. Then you got to assume variances are equal for everything. And then all of your samples are independent. Well, clearly, you know, things. Since you were assigned each all a different drug, you're probably all independent of each other. Anyway, and then, as always, this better be quantitative stuff, or else you can't do the ANOVA. If you're wondering how we deal with this when it's not quantitative, well, that's going to be Chi, which is next week. So I got factor A, factor B, and then my interaction factor, and these are how these always look. So what's interesting about this is you now have 3 hoes from one test. I warned you about this. Does it feel like Christmas? I don't know. Let's find out. Anyway, so for our dieting example, this would be, you know, product 1, product 2, and the placebo are all the same on average. For factor B with our diet example, on average, males, females, and non-binary folks all lose the same weight. And then the interaction factor would be that factor A and factor B do not interact in a way that will cause the mean response to be different. So this is saying that if I look at, you know, drug given and gender, they do not cause each other to have a different response. And this is something that's really interesting because, as you know, males, females, and those who identify as a non-binary gender might react differently to different drugs due to their body chemistry. So what's interesting about this is that interaction factor is completely necessary because you could be looking at something that totally changes those two. Good times. Makes me think of the time my husband and I went on a diet and he gave up soda and I gave up soda and he lost 20 pounds and nothing happened to me. I wanted to kill him. Anyway, so assuming that you noticed there were 3 hoes, there's 3 Fs. Woohoo! And they're all calculated the same way all of them have been before. We separate them by their groups. We calculate their mean square difference. Sorry, their sum of squares. Then we do the mean, and that's where this all is going to come from. Now, the only difference here is that error group is what's going to always make your quotient. So when we're doing these calculations, it's always your MS divided by your MS divided by your error, and then your MS divided by your error to make your F ratios. Let's look at the table more. Here are the formulas for how you do all of that. Again, I don't advocate you do this by hand. It's horrid. It's very bad. I'm not sure any of you will understand this. You don't have to. Minitab is going to do it for you. Oh, I forgot there was a second one of these. I really hope you are going to use technology to do this, because boy, do I not want to do this by hand. I have nightmares from when I had to do it by hand as a student. Oh, this is probably going to give me bad dreams tonight. Haha. Okay, so factor A, factor B, factor C, same thing. If my F is too big, we gonna reject. They all have different degrees of freedom, so be careful. Although these are all named F alpha, they're all going to be different F alphas. Good times. That. I really don't want to do this. Okay, so let's look at an airline that's offering incentives for different age groups based on the accumulated vacation time that they can receive. So we've got, is it 4 age groups? Yep. Oh my gosh. And then there are different value options that they give these individuals: cash option, vacation, or shopping. And then in each of these squares are the people's behavior with how much that they spent based on these incentives. So we want to see, does like this group the same as like, so if I'm looking just within the cash option groups, I'm comparing factor A. Does this box look the same as this box? Because that would be ignoring age group. Or it could be that I'm asking myself is, no wait, the same as this box, that's ignoring age group. And then comparing this group to this group would be like, hey, are these two age groups different for the cash option? And then, you know, similarly, yada, yada, yada. So it's kind of like, I'm going to check to see, are my rows the same? Okay, are my rows the same? Does age group have an effect on spending? Are my columns the same? Does the option I give them for what they get as their incentives the same? Or is it a combination of those two? Do old people like shopping more than young people? And that's when you're looking at combinations. This looks like a mess. Anyway, so if you do the summary statistics for all of these, you're looking at this kind of thing. I don't recommend you read this. We're going to pay attention to the Anova table, because I'm worried that a bunch of you are going to be like, oh, well, look, you know, this mean is the same as this mean, and where's the other one that's the same? And this one's really close, so those two are all equal. Don't do that, please. That is absolutely not what this test is doing. That's saying the samples are the same, which is not what tests do. We're looking to see, is the population the same? That's the whole point of doing a hypothesis test. Okay, so again, select Anova two-factor replication off that data analysis one. And again, if you haven't downloaded the data analysis pack, it's super easy to do. You can probably get it by Googling. Most versions of Excel have it on there. Yep, got to re-record this. Okay, so looking at these p-values, hopefully you see they're all fairly small, so I'm anticipating we're going to be rejecting everything here. And when looking at the critical values, hopefully you'll see that that's as true as well. It appears that age group, aka sample, didn't have any effect on what was going on here, on what people preferred. It appears that the columns that were made, aka the program offer or the incentives we were giving, didn't have an effect either. And then when I combined them, which was that interaction term, it appeared that that did nothing as well. So this is just like the general version of that. The incentives, age group, and interaction of the three appeared to not have any difference. We didn't reject any hose. It looks like everything's the same. Doesn't matter which one you do. So if you are the company making this decision, what you should say is, okay, which one was the cheapest for us to do and produce the biggest change in sales? Because that's the one you should do, not because they're not going to have any different effect on all these people. So if there was one that was super cheap, that's the one you should do. All right. Lastly, if it turned out there was an interaction, we need to do an interaction test. One way you can get around that is to do one-way ANOVAs to each test level and then for each factor. This is not something that I advocate you do. It is more work than what's necessary. Yeah. But obviously, in our example with the age groups and the incentives, we had no interaction, so we wouldn't do this. Um, so looking back, we're like, oh, it looks like the interaction is not present, so we wouldn't have to do that, as I just said. Why didn't I put this sooner? Anyway, so here's another way you can ask yourself, is there certain groups that are interacting with each other? These are called interaction plots. So when you have no interaction between them, everybody will look parallel, which is the first one. And if there is interaction present, they will cross. So in particular, like these three interact with each other because they cross, these two interact with each other because they cross, these two interact with each other, these two interact with each other, and these two interact with each other. So in particular, if you had, looking at your four groups, only two of them crossing, then you would say, aha, here are the two that are interacting with each other. But in this one that I've drawn here, everybody's got some sort of interaction they're having happen, which is usually not what happens. I believe this is actually my last slide. Okay, so if this was horrible and you're super worried, here's what you need to take from this. If I have more than one mean I want to compare, I need an ANOVA. If I have more than one category I want to compare for two different categorical variables on a quantitative response, I also need an ANOVA, but that one will be either a two-factor or a balanced. That's where we're at. Hopefully, Minitab will make this be a little bit better. Remember, it's a video. You can rewatch the parts you're confused about, and you can ask questions in office hours. I will be having lots of them. Hope this wasn't so horrible for you. That was not the last title. Why do I have this in here 3 times?